Right now, as you're listening to these words, something extraordinary is happening. You're experiencing what we call the present moment, that razor-thin slice between past and future that seems so real, so immediate, so undeniably there. But what if I told you that this moment, this very sensation of now, might be nothing more than an elaborate illusion? What if the flow of time itself, that most fundamental aspect of your existence, doesn't actually exist at all? Take a deep breath. Let yourself settle in. For the next while, allow yourself to forget about deadlines, schedules, and the relentless march of minutes and hours that typically govern your day, because today, we're going to explore one of the most mind-bending possibilities that modern science has to offer, that time, as we experience it, might not be real. The physicist Carlo Rovelli once observed that when we examine the universe at its most fundamental level, time simply disappears from the equations. Not metaphorically, not approximately, but literally vanishes. This isn't the musings of a philosopher or the speculation of a science fiction writer. This is cutting-edge physics, backed by some of the most brilliant minds of our time, suggesting that our most basic assumption about reality might be fundamentally wrong. But before we dive into the deep waters of theoretical physics and quantum mechanics, let's start with something simpler, something that's been troubling thinkers for thousands of years. Picture yourself standing on a train platform, watching an express train thunder past at incredible speed. From your perspective, the train is moving, and you are stationary. But now imagine you're on that train, looking out the window at the platform. Suddenly, it's the platform that appears to be racing backward, while you feel perfectly still. This simple observation gets to the heart of something profound. Motion, one of the most basic concepts in physics, is relative. There's no absolute reference frame, no cosmic judge that can definitively say what's moving and what's not. Now, if motion is relative, what about time? After all, time and motion are intimately connected. When we measure time, we're really measuring the motion of something, the hands of a clock, the vibration of atoms, the rotation of the earth. So if there's no absolute motion, could there also be no absolute time? This question has haunted physicists for over a century, ever since a young patent clerk named Albert Einstein began to seriously consider what would happen if we took the idea of relativity to its logical conclusion. What he discovered would fundamentally change our understanding of reality itself. But Einstein wasn't the first to question time's reality. The ancient Greek philosopher Parmenides argued that change itself was an illusion, that reality was eternal and unchanging. His student Zeno created paradoxes that seemed to prove motion was impossible. If you wanted to walk across a room, Zeno argued, you'd first have to cross half the distance, then half of what remained, then half of that, and so on, creating an infinite series of tasks that could never be completed. For over 2 millennia, these puzzles were dismissed as clever word games, philosophical curiosities, with no bearing on the real world. But as we'll see, modern physics has begun to take these ancient ideas seriously, finding in them echoes of profound truths about the nature of reality. The first crack in time's facade appeared in the 19th century, when physicists began to seriously study light. They discovered that light travels at a specific speed, roughly 300 million meters per second, and that this speed seemed to be constant regardless of how you measured it. This was deeply puzzling. Imagine you're in a car traveling at 60 miles per hour and you throw a ball forward at 30 miles per hour. To someone standing on the sidewalk, that ball appears to be moving at 90 miles per hour. This is simple addition, the way velocities are supposed to work. But light doesn't behave this way. Whether you're standing still or racing toward a source of light at tremendous speed, you always measure light traveling at the same velocity. It's as if the universe has a built-in speed limit that nothing can exceed, and this limit is somehow woven into the very fabric of space and time. Einstein realized that if the speed of light is truly constant, then something else must be variable, time itself. In his theory of special relativity, Einstein showed that time is not the universal, absolute backdrop that Newton had imagined. Instead, time is flexible, stretching and compressing depending on how fast you're moving. Consider two identical twins, Sarah and Emma. Sarah stays on Earth while Emma takes a journey to a nearby star at a speed close to the speed of light. When Emma returns, she will have aged less than Sarah. Not metaphorically, not in some abstract sense, but literally. Emma's clocks will show less elapsed time, her body will have undergone fewer cellular divisions, her heart will have beaten fewer times. From Emma's perspective, she experienced time normally, but the universe conspired to make her journey take less time than it should have. This isn't science fiction. It's been measured with atomic clocks, observed in particle accelerators, and verified in countless experiments. Time dilation is as real and measurable as the weight of a stone or the temperature of water, but special relativity was just the beginning. Einstein's general theory of relativity revealed something even more startling. Gravity doesn't just affect objects, it affects time itself. The stronger the gravitational field, the slower time moves. If you were to stand next to a black hole, time would crawl compared to someone far away from any massive objects. This isn't just theoretical, it's practical. The satellites that power GPS systems have to account for the fact that time moves slightly faster in orbit than it does on Earth's surface. Without these relativistic corrections, your GPS would be off by miles within hours. So we have a universe where time moves at different rates, depending on where you are and how fast you're moving. But surely, you might think, there's still an objective sequence of events, a universal now that everything shares. Not according to relativity. Imagine two events happening far apart in space, a star exploding in a distant galaxy and a child being born on Earth. In some reference frames, the star explosion happens first. In others, the birth happens first. There's no universal answer to which event actually occurred first. The concept of simultaneity, of a shared present moment, is purely local. This leads to what physicists call the block universe theory. If there's no universal now, no objective present moment, then past, present, and future must all exist equally. The universe isn't a movie with frames flickering by, but more like a completed sculpture, where every moment that ever was or ever will be exists simultaneously in what Einstein called the space-time continuum. From this perspective, your birth, your death, and every moment in between already exist, frozen like frames in an eternal film strip. You don't move through time. Instead, your consciousness experiences different slices of your world line, creating the illusion of flow and change. The implications are staggering. If the block universe theory is correct, then everything that will ever happen has, in some sense, already happened. Your future self exists right now, just as much as your past self. The conversation you'll have tomorrow, the decision you made yesterday, the book you read as a child, all of these exist simultaneously in the four-dimensional structure of space-time. But wait, if this is true, what about free will? If your future actions already exist, carved into the structure of space-time, are you really making choices, or are you simply following a predetermined script? This question touches on one of the deepest mysteries in physics and philosophy. Some argue that free will is compatible with a block universe, that your choices are real and meaningful even if they exist timelessly. Others suggest that free will itself might be an illusion, a byproduct of our limited perspective on a deterministic universe. Yet even as relativity was revolutionizing our understanding of time, another revolution was brewing in the quantum realm. Quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales, introduced a new kind of strangeness that would make Einstein's relativity seem almost quaint by comparison. In the quantum world, particles don't have definite positions or velocities until they're measured. They exist in what physicists call superposition, a ghostly state where they're simultaneously in multiple places or moving at multiple speeds. When we measure a quantum system, we don't just observe its properties, we actually create them, collapsing the superposition into a single, definite outcome. This raises profound questions about the nature of time in the quantum realm. If particles don't have definite properties until they're measured, What does it mean for them to evolve through time? Some interpretations of quantum mechanics suggest that the entire history of a quantum system exists in superposition until an observation collapses it into a single timeline. Consider Schrödinger's famous thought experiment with the cat that's simultaneously alive and dead until observed. If we take this seriously, then the cat's entire timeline, its birth, its life, its death, might exist in superposition, becoming definite only when consciousness enters the picture. This leads to even more radical ideas about time. Some physicists propose that time itself might be emergent, arising from the collective behavior of quantum systems rather than being fundamental to reality. Just as temperature emerges from the random motion of molecules without being a property of any individual molecule, time might emerge from quantum processes without being woven into the basic fabric of reality. The physicist John Wheeler suggested that we live in a participatory universe where consciousness plays a fundamental role in creating reality through the act of observation. If Wheeler is right, then not only is time not real in any objective sense, but the past itself might be determined by present observations. Wheeler proposed delayed choice experiments where the decision of what to measure can apparently reach backward in time to influence what happened in the past. These aren't just thought experiments. They've been performed in laboratories, and the results support Wheeler's strange predictions about the relationship between consciousness and reality. But quantum mechanics presents another puzzle about time, the problem of measurement. When a quantum system interacts with a measuring device, its superposition collapses instantaneously. This collapse appears to happen outside of time, in a single moment that has no duration, yet the equations of quantum mechanics are time-symmetric. They work equally well backward and forward in time. So why do we observe collapse in one direction but not the other? This asymmetry is related to one of the deepest mysteries in physics: why time seems to have an arrow, a direction from past to future. The fundamental laws of physics, whether quantum mechanics, relativity, or the standard model of particle physics, are largely time-symmetric. They work equally well backward and forward in time, yet our experience of time is profoundly asymmetric. We remember the past, but not the future. We see eggs break, but never spontaneously reassemble. We age, but never grow younger. The answer, according to most physicists, lies in thermodynamics, the science of heat and energy. The second law of thermodynamics states that entropy, a measure of disorder, always increases in isolated systems. This gives time its arrow, from lower entropy to higher entropy, from order to disorder. But this raises a new puzzle. If the universe is gradually becoming more disordered, it must have started in a state of extremely low entropy. The early universe must have been remarkably ordered, with all its energy and matter arranged in an almost impossibly unlikely configuration. Why was the universe born in such an ordered state? Some cosmologists suggest that our universe is just one of many, that the multiverse naturally gives rise to regions of low entropy that evolve into universes like ours. Others propose that the initial conditions of our universe were set by unknown physical processes that we haven't yet discovered. But there's another possibility, one that brings us back to the question of whether time is real. Perhaps the arrow of time isn't fundamental, but emergent, arising from the way conscious observers process information. Perhaps what we call the past is simply the subset of information that we've processed, while the future represents information that remains unprocessed. This connects to recent work in theoretical physics on the relationship between information and thermodynamics. In the 1970s, Stephen Hawking discovered that black holes have temperature and entropy, and that they gradually evaporate by emitting radiation. This led to the realization that information and energy are deeply connected, and that the processing of information might be fundamental to the nature of reality itself. Some physicists now propose that space-time itself might be made of information, that the geometry of the universe emerges from the way information is organized and processed. If this is true, then time might not be a stage on which events unfold, but rather a byproduct of information processing, no more fundamental than the concept of a file directory on a computer. Another possibility is that what we call change is really just the exploration of relationships that already exist in a timeless reality. When a flower grows, it's not creating something new in time, but revealing a pattern that exists eternally in the space of all possible configurations. The physicist Lee Smolin has argued against these timeless approaches, proposing instead that time is real and fundamental, and that the laws of physics themselves evolve through time. Smolin suggests that what we consider eternal laws might actually be habits of the universe, patterns that have evolved through cosmic natural selection. But even Smolin's approach faces challenges from quantum mechanics and relativity. If time is fundamental, why does it behave so differently at different scales and in different circumstances? Why does it slow down in strong gravitational fields and speed up for fast-moving objects? Why does it seem to disappear entirely in the quantum realm? The answer might lie in the fact that we're asking the wrong question. Instead of asking whether time is real or not, we might need to ask what we mean by reality itself. In quantum mechanics, particles don't have definite properties until they're measured. In relativity, simultaneity is relative to the observer. In thermodynamics, the arrow of time emerges from statistical processes. Perhaps reality itself is not fixed and objective, but depends on the perspective of the observer. Perhaps time is real for conscious beings embedded in the universe, but not real from a God's eye view that encompasses all of space-time simultaneously. This might explain why physics seems to be moving toward a picture of reality where information and consciousness play fundamental roles. If reality depends on observation and information processing, then time might be real for observers, but not exist independently of them. Recent experiments in quantum mechanics support this interpretation. The physicist Anton Zeilinger and his colleagues have demonstrated that the properties of quantum systems can depend on future measurements, not just past interactions. They've shown that what we choose to measure can apparently influence what happened in the past, suggesting that the relationship between time and causality is far stranger than our everyday experience suggests. These experiments hint at a universe where time is not a stage on which events unfold, but rather an emergent property of the relationship between consciousness and quantum systems. From this perspective, time exists because we observe and measure, not as an independent backdrop to reality. But this raises new questions about the nature of consciousness itself. If consciousness is necessary for time to exist, what is consciousness? Is it something that emerges from complex arrangements of matter, or is it fundamental to the universe itself? Some physicists, following in the footsteps of Wheeler and Stapp, propose that consciousness is indeed fundamental, woven into the basic structure of reality alongside matter and energy. This approach, sometimes called panpsychism, suggests that all particles have some rudimentary form of consciousness, and that complex awareness emerges from the interaction of these simple conscious elements. If consciousness is fundamental, then the universe might be far stranger than we imagine. Rather than being a collection of unconscious matter moving through space-time, reality might be a network of conscious interactions, with time emerging from the way these conscious elements process information and make measurements. This connects to some of the most speculative ideas in modern physics, such as the holographic principle and the suggestion that the universe is a kind of cosmic computer, processing information and generating the experience of space-time as output. The physicist John Wheeler once suggested that the universe is made of information, that it from bit describes the fundamental nature of reality. If Wheeler is right, then space, time, matter, and energy are all different aspects of information processing, different ways that the universe computes itself into existence. From this perspective, time becomes not a dimension like space, but more like the CPU clock of a cosmic computer, the rhythm at which information is processed and reality unfolds. Our experience of temporal flow would then be analogous to the way a computer program executes, with each moment corresponding to a computational step in the universe's ongoing calculation of itself. This information-theoretic approach to physics has led to some remarkable insights. The physicist Leonard Susskind has shown that the information content of any region of space is proportional to the area of its boundary, not its volume. This suggests that what we perceive as three-dimensional space might actually be encoded on a two-dimensional surface, like a hologram. If space is holographic, what about time? Some researchers are exploring the possibility that time itself might be holographic, that what we experience as temporal flow might be encoded in a timeless substrate. The physicist Julian Barber has proposed that time emerges from the relationships between different configurations of matter and energy without being fundamental to reality. Barber's approach treats the universe as a collection of possible arrangements of matter, what he calls the space of all possible nows. Time emerges from the way these configurations relate to each other, creating the illusion of change and flow without requiring time to be woven into the fabric of reality. This connects to some of the most advanced theories in modern physics, such as loop quantum gravity and string theory. Loop quantum gravity suggests that space and time are made of discrete quantum building blocks, and that time might emerge from the statistical behavior of these quantum units. String theory proposes that all fundamental particles are vibrating strings in higher dimensional space, and that time might be just another spatial dimension that we experience differently due to our limited perspective. Both of these approaches suggest that time as we experience it is not fundamental, but emergent, arising from more basic physical processes that operate outside of time entirely. But perhaps the most radical challenge to time's reality comes from the study of consciousness itself. Our experience of time is intimately connected to our awareness, to the stream of consciousness that seems to flow from moment to moment. But what if consciousness, like time, is not what it seems? Neuroscientists have discovered that our brains don't process information in real time, but construct the experience of now from multiple sensory inputs that arrive at different times. When you see a person speaking, your brain synchronizes the visual and auditory information to create the illusion of simultaneity, even though light travels much faster than sound. Similarly, our sense of the present moment isn't instantaneous, but extends over a period of several seconds, during which the brain integrates information to create what psychologists call the specious present. This suggests that even our most immediate experience of time is constructed rather than directly perceived. Some researchers go further, proposing that consciousness itself might be the source of time's arrow. The physicist Henry Stapp suggests that the collapse of quantum superpositions requires consciousness, and that this collapse is what creates the flow of time. From this perspective, time doesn't exist without conscious observers to collapse quantum states and create definite outcomes. This idea connects to ancient philosophical traditions that have long questioned the reality of time. Buddhist philosophy speaks of the eternal present, a timeless awareness that underlies the apparent flow of moments. Hindu philosophy describes time as Maya, illusion, a veil that obscures the timeless nature of reality. These traditions suggest that time is a product of limited perception, that from a higher or more complete perspective, all of reality exists in an eternal now. Modern physics, with its block universe theory and quantum mechanics, seems to be converging on similar conclusions through entirely different routes. But if time isn't real, how do we explain the obvious changes we observe in the world around us? How do we account for growth, decay, birth, death, and all the processes that seem to require temporal flow? One answer is that change doesn't require time in the way we normally think about it. Consider a film strip. Each frame is static, unchanging, yet when viewed in sequence, they create the appearance of motion and change. Similarly, the block universe might contain static arrangements of matter and energy that, when experienced sequentially by consciousness, create the appearance of temporal flow. But even this computational approach faces challenges. If the universe is computing itself, what is it computing on? What provides the hardware for this cosmic information processing? Some physicists suggest that the answer lies in the quantum vacuum itself, the seething sea of virtual particles and fields that fills apparently empty space. The quantum vacuum is far from empty. It's alive with activity, constantly creating and destroying virtual particles in accordance with quantum mechanics. Some researchers propose that this vacuum activity provides the computational substrate for reality, that space-time emerges from the information processing occurring in the quantum foam. If this is true, then time might not be woven into the fabric of reality, but might instead emerge from the computational activity of the quantum vacuum. The vacuum would be timeless, but its information processing would create the illusion of temporal flow for embedded observers. This approach connects to recent work on emergent gravity, the idea that gravity itself might not be fundamental, but might emerge from more basic quantum processes. If gravity can emerge from quantum mechanics, perhaps time can as well. The physicist Eric Verlinde has proposed that gravity emerges from the tendency of information to spread out and become more evenly distributed, similar to the way heat flows from hot objects to cold objects. If Verlinde is right, then both gravity and time might be thermodynamic phenomena emerging from the statistical behavior of quantum information. This would explain why time's arrow is connected to entropy and why gravitational time dilation occurs. Both would be aspects of the same underlying process, the universe's tendency to maximize information entropy and minimize energy gradients. But this raises new questions about consciousness and observation. If time emerges from information processing, what role does consciousness play in this process? Are conscious observers special, or are they just particularly complex information processing systems embedded within the cosmic computation? Some researchers suggest that consciousness is indeed special, that it provides a kind of reference frame that allows time to emerge from timeless quantum processes. From this perspective, time exists because conscious observers collapse quantum superpositions and create definite outcomes. Others propose that consciousness is not special, but is simply one type of information processing among many. From this view, time emerges whenever any system processes information, whether conscious or not. A rock falling toward the ground is processing information about the gravitational field, and this information processing contributes to the emergence of time. This connects to the concept of integrated information theory, developed by the neuroscientist Giulio Tononi. Tononi proposes that consciousness corresponds to integrated information, the degree to which a system processes information as a unified whole rather than as separate parts. If consciousness is integrated information, then the universe might be filled with varying degrees of consciousness, from the minimal integration of simple particles to the complex integration of human brains. Time might emerge from this cosmic information integration, with more complex systems experiencing richer temporal flows. But even as we explore these speculative ideas about consciousness and information, we must remember that science progresses through experiment and observation, not just theory. What experimental evidence do we have for the unreality of time? The most direct evidence comes from particle physics experiments that measure the lifetime of unstable particles. When these particles travel at high speeds, their lifetimes are extended exactly as predicted by special relativity. Time dilation is not just theoretical, but measurable and practical. Similarly, gravitational time dilation has been measured with extraordinary precision using atomic clocks. When atomic clocks are moved to different altitudes, they tick at different rates in exactly the way predicted by general relativity. The effect is small, but measurable. A clock on a mountaintop runs about 30 nanoseconds per day, faster than an identical clock at sea level. Quantum mechanics provides more subtle but equally compelling evidence for the strangeness of time. Experiments with quantum entanglement show that measurement of one particle can instantly affect its entangled partner, regardless of the distance between them. This apparent faster-than-light connection doesn't allow for communication, but it does suggest that the relationship between cause and effect is not as straightforward as our everyday experience suggests. The delayed choice experiments pioneered by Wheeler and others provide even stranger evidence. These experiments suggest that what we choose to measure in the present can influence what happened in the past. While the interpretation of these experiments remains controversial, they certainly challenge our conventional understanding of temporal causality. Perhaps most compelling are the experiments that test Bell's theorem, which shows that quantum mechanics is incompatible with local realism, the idea that objects have definite properties independent of observation and that influences cannot travel faster than light. The violation of Bell's inequalities in laboratories around the world demonstrates that reality is fundamentally non-local and observer-dependent in ways that challenge our classical notions of space and time. But experimental evidence is just one part of the picture. Theoretical physics provides additional reasons to question time's reality. The equations of quantum gravity, whether formulated through loop quantum gravity, string theory, or other approaches, suggest that time as we know it, it breaks down at the smallest scales and highest energies. Near the Big Bang, according to current theories, space-time itself becomes quantum mechanical and subject to the uncertainty principle. The very concepts of before and after lose meaning when space-time fluctuates quantum mechanically. This suggests that time, rather than being eternal and unchanging, had a beginning and might have an end. Some cosmologists propose that time is cyclic, that the universe goes through repeated cycles of expansion and contraction, with time flowing forward during expansion and backward during contraction. Others suggest that time branches like a tree, with multiple timelines emerging from quantum processes and conscious observations. The physicist Sean Carroll has proposed that the arrow of time emerges from the special initial conditions of our universe, that the Big Bang created a state of low entropy that has been increasing ever since. As entropy approaches its maximum value, time's arrow might weaken or disappear entirely, leading to a universe where past and future become indistinguishable. But perhaps the most profound challenge to time's reality comes not from physics, but from philosophy. The philosopher Henri Bergson argued that scientific time, the time of clocks and equations, is different from lived time, the time of experience and consciousness. Bergson suggested that scientific time is a spatial representation of temporal flow, useful for calculation, but missing the essential quality of time as experienced. This distinction between scientific time and experiential time has been explored by phenomenologists like Edmund Husserl and Martin Heidegger, who argued that temporal experience is fundamental to consciousness and cannot be reduced to physical processes. From this perspective, even if physical time is illusory, temporal experience remains real and irreducible. The tension between scientific and experiential approaches to time reflects a deeper question about the relationship between objective and subjective reality. Does consciousness reveal aspects of reality that are missed by physical science, or is consciousness itself part of the physical world and subject to scientific explanation? Some philosophers argue that the hard problem of consciousness, the question of how subjective experience arises from objective physical processes, is intimately connected to the problem of time. If consciousness cannot be explained in purely physical terms, then perhaps time, as an aspect of conscious experience, cannot be either. Others suggest that both consciousness and time will eventually be explained by physics, once we develop a more complete understanding of quantum mechanics and its relationship to macroscopic phenomena. From this perspective, the apparent mystery of time is just a reflection of our current ignorance, not evidence for anything beyond the physical world. But as our scientific understanding has advanced, the mystery of time has deepened rather than resolved. Each new discovery, from relativity to quantum mechanics to cosmology, has revealed new aspects of time's strangeness. Rather than clarifying what time is, science has made it more mysterious and problematic. This might be telling us something important about the nature of reality itself. Perhaps the mystery of time is not a problem to be solved, but a fundamental aspect of existence. Perhaps time is the interface between the physical world and consciousness, the medium through which subjective experience emerges from objective processes. From this perspective, the question of whether time is real becomes not a scientific question, but an existential one. Time is real for us because we are temporal beings, embedded in the flow of change and becoming. Even if time is not woven into the fundamental structure of reality, it emerges from our interaction with that reality, making it real in the only sense that matters for conscious beings. This doesn't diminish the importance of scientific investigations into time's nature. Understanding how time emerges from timeless processes, how consciousness interfaces with quantum mechanics, and how information gives rise to space-time are crucial questions that will deepen our understanding of reality. But it does suggest that these scientific questions will not eliminate the existential dimension of temporal experience. The block universe theory, if correct, tells us that your future self exists just as much as your present self, but it doesn't change the fact that you must still make choices, still navigate uncertainty, still experience the flow from moment to moment. Even in a timeless universe, life remains temporal for those living it. Similarly, quantum mechanics might tell us that reality is observer-dependent and non-local, but it doesn't change the fact that observations occur in sequence, that causes generally precede effects in our experience, and that we remember the past but not the future. Even if time emerges from timeless quantum processes, those processes give rise to thoroughly temporal creatures like ourselves. The philosophical implications of time's possible unreality are profound and far-reaching. If time is not fundamental, what does this mean for concepts like mortality, progress, history, and hope? How do we understand change, growth, and development if time itself is illusory? One response is to recognize that emergence can be as real as anything else. The temperature of a gas emerges from molecular motion, but it's still real and meaningful. The solidity of a table emerges from electromagnetic forces between atoms, but the table is still solid. Similarly, time might emerge from timeless processes while remaining real and meaningful for temporal beings. Another response is to embrace the mystery and strangeness of reality. Perhaps the universe is far weirder than we can imagine, operating according to principles that transcend our everyday categories of understanding. Perhaps time's mystery is a reminder of how much we don't know, how much reality exceeds our current comprehension. The scientist J.B.S. Haldane once observed that the universe is not only stranger than we imagine, it is stranger than we can imagine. This might be particularly true of time, which is so fundamental to our experience that we have difficulty stepping outside it to see it objectively. But perhaps this difficulty is itself instructive. Perhaps time's centrality to consciousness tells us something important about the nature of both. Perhaps conscious beings are necessarily temporal beings, embedded in the flow of change and becoming in ways that make time real, regardless of its ultimate physical status. This connects to recent work in cognitive science on the relationship between consciousness and time. Researchers have found that our sense of temporal flow is constructed by the brain from multiple sensory inputs and memory processes. The present moment, rather than being instantaneous, extends over several seconds and involves complex integration of information from different time scales. Some researchers propose that consciousness itself is fundamentally temporal, that the unity of conscious experience depends on the integration of information over time. From this perspective, time is not just experienced by consciousness, but is constitutive of consciousness itself. If consciousness is necessarily temporal, then the reality of time might depend on the reality of consciousness. This brings us back to the fundamental questions about the relationship between mind and matter, between subjective experience and objective reality. The physicist Eugene Wigner suggested that consciousness plays a fundamental role in quantum mechanics, that the collapse of quantum superpositions requires conscious observation. While this interpretation remains controversial, it highlights the deep connections between consciousness, observation, and physical reality. Recent experiments in quantum mechanics have shown that the mere presence of a detector, whether conscious or not, can affect quantum systems. This suggests that information, rather than consciousness per se, plays the key role in quantum processes. But it leaves open the question of what distinguishes conscious from unconscious information processing. Some researchers propose that consciousness corresponds to integrated information that is processed as a unified whole rather than as separate parts. Others suggest that consciousness involves recursive self-awareness, the ability of a system to model itself and its own states. If consciousness involves self-modeling, then perhaps time emerges from the way conscious systems model their own temporal experience. The flow of time might be a byproduct of the way consciousness represents change and sequence to itself. This would explain why time seems so central to conscious experience while being problematic in fundamental physics. Time might be real for conscious systems because it's built into the way they represent reality, even if it's not woven into the fabric of reality itself. But this raises new questions about the evolution and development of consciousness. If consciousness is responsible for time's reality, how did conscious systems evolve in the first place? How can temporal beings emerge from supposedly timeless processes? One answer is that consciousness and time co-evolve, that neither is more fundamental than the other. As information processing systems become more complex, they develop more sophisticated models of temporal sequence, which in turn allow for more complex conscious states. From this perspective, simple systems like bacteria or plants might have rudimentary temporal experience corresponding to their basic information processing capabilities. More complex systems like mammals develop richer temporal experience, including memory, anticipation, and planning. Humans, with our sophisticated brains and language capabilities, experience the richest temporal flow, including abstract concepts like history, progress, and possibility. This evolutionary approach to consciousness and time suggests that reality itself might be evolving, becoming more complex and conscious over time. Rather than time being fundamental or completely illusory, it might be an emerging feature of an evolving universe, becoming more real as consciousness becomes more complex. The physicist Freeman Dyson has speculated about the ultimate fate of consciousness in an expanding universe. As the universe cools and expands, stars will burn out and black holes will evaporate, leaving only elementary particles scattered across vast distances. But Dyson suggests that consciousness might survive even these cosmic changes, processing information more slowly but continuing indefinitely. If Dyson is right, then consciousness and time might persist, even in the far future, evolving new forms appropriate to the changed conditions of the universe. Time would remain real for conscious beings, even in a universe drastically different from our own. But other cosmologists suggest different scenarios. Some propose that the universe will eventually reach a state of maximum entropy, where no further information processing is possible. In such a heat-death scenario, consciousness and time would both disappear, leaving only a static, changeless void. Still others suggest that the universe might be cyclic, going through repeated phases of expansion and contraction. In such scenarios, consciousness and time might disappear during contracting phases only to re-emerge during expanding phases, creating an eternal cycle of awakening and sleep. These cosmological speculations remind us how much we still don't know about the ultimate nature of reality. Despite centuries of scientific progress, fundamental questions about space, time, consciousness, and existence remain largely unanswered. But perhaps this is as it should be. Perhaps mystery is a fundamental aspect of existence, not a temporary condition to be overcome by scientific progress. Perhaps the question of whether time is real will always remain partially open, accessible to investigation, but never fully resolved. This doesn't mean that scientific investigation is pointless. Each new discovery about time, consciousness, and reality adds to our understanding and opens new avenues for exploration. But it does suggest that some questions might be more important for their asking than for their answering, more valuable for the journey of investigation than for any final destination. The question of time's reality is one such question. It forces us to examine our deepest assumptions about existence, to consider the relationship between subjective experience and objective reality, to grapple with the mystery of consciousness in a physical universe. Whether time is real or illusory, fundamental or emergent, the investigation itself is valuable. It expands our understanding of reality and our place within it. It connects us to the deepest traditions of human inquiry, from ancient philosophy to modern physics. And perhaps most importantly, it reminds us of the profound strangeness of existence itself. We are conscious beings in a universe that might be stranger than we can imagine, experiencing a flow of time that might not be woven into reality's fabric. This is not a cause for despair, but for wonder, not a problem to be solved, but a mystery to be explored. As you continue through your day, through the apparent flow of moments that carry you from past to future, remember that this experience might be far stranger than it seems. You might be a temporal pattern in a timeless universe, a conscious observer creating the flow of time through the very act of observation. The ancient philosopher Heraclitus said that no one steps in the same river twice, for it is not the same river and they are not the same person. But modern physics suggests something even stranger. There might be no river at all, no flow of time in which stepping could occur. There might only be the eternal pattern of water and stones, conscious observers and quantum fields, creating the illusion of flow through the mystery of awareness itself. Whether this is true or not, whether time is real or illusory, the mystery remains. And in that mystery lies something precious, the ongoing adventure of consciousness encountering reality, the eternal human quest to understand our place in the cosmos, the timeless search for truth in a universe that might itself transcend time. This is the gift of the question. Regardless of its answer, it awakens us to the profound mystery of existence and our privileged position as conscious observers in a possibly timeless universe. But let's delve deeper into this mystery, exploring the intricate ways that modern science continues to challenge our most basic assumptions about temporal reality. Consider the strange world of quantum field theory, where particles are understood not as little billiard balls moving through space, but as excitations in underlying fields that permeate all of reality. In this picture, an electron is not a thing that moves through time, but a temporary pattern in the electron field, like a wave on the ocean's surface. The wave appears to move, but it's really just a traveling disturbance in a medium that extends throughout space. If particles are field excitations rather than objects, what does this mean for their relationship to time? The fields themselves exist throughout all of space-time simultaneously. An electron appearing here and now is connected to the electron field everywhere and everywhen. The apparent motion of the particle through time might be more like the apparent motion of a wave, a pattern that seems to flow but is really a static structure in the underlying field. This field theoretic picture becomes even stranger when we consider virtual particles, the ghostly entities that quantum mechanics tells us are constantly appearing and disappearing in the vacuum of space. These virtual particles exist for such brief moments that they cannot be directly observed, yet they have measurable effects on the behavior of real particles. They mediate all the fundamental forces, carrying the electromagnetic, weak, and strong interactions between particles. But here's the puzzle. Virtual particles violate conservation of energy. They borrow energy from the vacuum and must pay it back within a time interval determined by Heisenberg's uncertainty principle. The more energy they borrow, the shorter their allowed lifetime. This creates a strange relationship between energy and time that seems to exist outside of our normal temporal framework. In the quantum vacuum, cause and effect become blurred. A virtual photon can be absorbed by an electron before it was emitted by another electron. The usual temporal ordering of cause and effect breaks down at the quantum level, suggesting that time as we understand it is not fundamental to the deepest level of physical reality. This connects to some of the most puzzling aspects of quantum mechanics, such as the EPR paradox discovered by Einstein, Podolsky, and Rosen. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance and argued that it proved quantum mechanics was incomplete, but subsequent experiments have confirmed that quantum entanglement is real. When Alice measures the spin of her particle in one location, Bob's entangled particle in a distant location instantly acquires the opposite spin. This happens faster than light could travel between the two locations, suggesting that the connection transcends space and time as we normally understand them. Some interpretations of quantum mechanics propose that entangled particles are connected outside of spacetime through what physicists call the quantum mechanical state vector. This state vector exists in a mathematical space called Hilbert space, which has no direct correspondence to physical spacetime. From this perspective, the instant correlation between entangled particles doesn't involve faster-than-light communication, but reflects their connection in a timeless mathematical realm. If fundamental particles are connected through timeless mathematical structures, what does this say about the nature of time itself? Perhaps space-time is not the fundamental arena in which physics occurs, but rather an emergent approximation that applies only at certain scales and under certain conditions. This possibility is supported by recent work on the ADS-CFT correspondence, one of the most important developments in theoretical physics in the past few decades. This correspondence, discovered by Juan Maldacena, shows that certain theories of gravity in higher dimensional space can be exactly equivalent to quantum field theories without gravity in lower dimensions. The remarkable thing about ADS/CFT is that gravity and space-time on one side of the correspondence emerge from quantum field theory on the other side. Space-time is not fundamental, but arises from the entanglement structure of quantum fields. Time, as part of space-time, emerges from timeless quantum processes. This emergence of space-time from quantum entanglement has profound implications for our understanding of reality. If space-time is emergent rather than fundamental, then questions about what existed before the Big Bang or what lies beyond the edge of space become meaningless. There is no before or beyond in the timeless quantum realm from which space-time emerges, but emergence raises its own puzzles. How can something as seemingly fundamental as time emerge from timeless processes? How can temporal beings, like ourselves, arise in a universe where time is not basic? One answer comes from the study of complex systems and emergence. Just as wetness emerges from the interaction of H2O molecules that are not themselves wet, time might emerge from the interaction of timeless quantum processes. The key is that emergence often involves new properties and behaviors that cannot be reduced to the properties of the underlying components. Consider the emergence of biology from chemistry. Individual molecules are not alive, yet when they interact in sufficiently complex ways, life emerges. Similarly, individual quantum processes might be timeless, yet when they interact in sufficiently complex ways, time emerges along with the macroscopic world we inhabit. This emergence of time from timeless processes might explain why time seems so different at different scales. At the quantum scale, particles tunnel through barriers, exist in superposition, and correlate instantly across vast distances. At the macroscopic scale, objects follow well-defined trajectories, exist in definite states, and interact through local forces that respect the speed of light limit. The transition between these scales involves what physicists call decoherence, the process by which quantum superpositions collapse into definite classical states through interaction with the environment. Decoherence might not just explain the emergence of classical physics from quantum mechanics, but the emergence of time itself. When quantum systems interact with their environment, they lose their quantum coherence and begin to behave classically. This process creates definite outcomes from quantum probabilities and establishes the classical world of our everyday experience, but it might also create the flow of time as quantum superpositions collapse in a preferred direction determined by the increase of entropy. The physicist Max Tegmark has calculated how quickly decoherence occurs in typical environments. For macroscopic objects at room temperature, quantum coherence is destroyed in tiny fractions of a second. This suggests that our classical temporal world is constantly being recreated through the ongoing process of quantum decoherence. If time emerges from decoherence, then the arrow of time is not fundamental, but statistical, arising from the overwhelming probability that entropy increases rather than decreases. This would explain why time's arrow is connected to thermodynamics, and why it might weaken or reverse under extreme conditions. Some physicists have speculated about regions of the universe where entropy decreases rather than increases, creating regions where time flows backward relative to our experience. These time-reversed regions would be populated by beings who remember the future and anticipate the past, yet from their perspective, they would experience time flowing normally forward. Such speculation might seem like science fiction, but it's grounded in the time-symmetric nature of fundamental physical laws. If the laws of physics work equally well forward and backward in time, then regions of decreasing entropy are as valid as regions of increasing entropy. The direction of time's arrow would depend on local conditions rather than being fixed throughout the universe. This connects to recent work in cosmology on the multiverse, the idea that our universe might be one of many. If the multiverse is real, different regions might have different arrows of time, different rates of temporal flow, and different relationships between consciousness and time. In some regions of the multiverse, time might not emerge at all, leaving only timeless quantum processes. In others, time might emerge but flow in multiple directions simultaneously, creating complex temporal structures unlike anything in our experience. Our own region, with its single, forward-flowing temporal dimension, might be special only from our perspective as beings adapted to this particular temporal environment. But even within our own universe, the nature of time continues to surprise us. Recent observations of black holes have revealed phenomena that challenge our understanding of time and causality. When matter falls into a black hole, it appears to outside observers to slow down and stop at the event horizon, taking infinite time to actually cross the boundary. Yet, from the perspective of the falling matter, the crossing happens in finite time. This creates a puzzle about the information contained in the falling matter. From the outside perspective, the information remains forever frozen at the event horizon. From the inside perspective, the information disappears beyond the horizon and is eventually destroyed when it reaches the central singularity. Both perspectives seem valid, yet they give contradictory answers about what happens to information. Stephen Hawking's discovery that black holes evaporate through the emission of thermal radiation makes this puzzle even more acute. If black holes evaporate completely, what happens to the information that fell into them? Does it disappear from the universe, violating fundamental principles of quantum mechanics? Or is it somehow encoded in the Hawking radiation, preserving information in a highly scrambled form? Recent work by theoretical physicists suggests that the information is indeed preserved, but in ways that challenge our normal understanding of space and time. The information might be encoded on the event horizon itself, creating a holographic representation of everything that falls into the black hole. Or it might be connected to the Hawking radiation through quantum entanglement that transcends the black hole's event horizon. Either way, the resolution of the black hole information paradox seems to require an understanding of space-time that goes beyond our current concepts. Information might be more fundamental than space-time itself, with spatial and temporal relationships emerging from underlying information structures. This information-theoretic approach to physics has deep connections to computer science and information theory. Some physicists now propose that the universe is literally a computer, processing information according to quantum mechanical rules and generating space-time as output. The physicist Seth Lloyd has calculated the computational capacity of the universe, showing that since the Big Bang, the universe could have performed at most 10 to the power of 120 operations on at most 10 to the power of 90 bits of information. If the universe is computing itself into existence, these numbers represent the limits of what reality can contain. From this computational perspective, time becomes the clock cycle of the cosmic computer, the rate at which the universe updates its state. Our experience of temporal flow would correspond to our embeddedness in this cosmic computation, experiencing reality as it unfolds step by step through the universe's information processing. But this raises profound questions about the nature of computation and consciousness. If the universe is computing itself, what distinguishes this cosmic computation from other forms of information processing? What makes it conscious or real in ways that other computations are not? Some philosophers argue that all sufficiently complex computations are conscious, that consciousness is substrate independent and can arise in any system that processes information in the right way. If this is true, then artificial intelligence systems might eventually develop genuine consciousness and their own experience of temporal flow. Others maintain that consciousness requires something beyond mere computation, perhaps quantum processes in the brain that cannot be replicated in classical computers. From this perspective, consciousness and time might be intimately connected to quantum mechanics in ways that transcend computational approaches. Recent research in neuroscience has begun to shed light on these questions by studying how the brain creates our experience of time. Neuroscientists have discovered that time perception involves multiple brain regions and mechanisms, from millisecond timing in the cerebellum to circadian rhythms in the hypothalamus. Damage to specific brain regions can dramatically alter time perception. Patients with Parkinson's disease often experience disrupted timing, while those with schizophrenia may have distorted temporal processing. Drugs can also alter time perception, with stimulants making time seem to pass quickly and depressants making it crawl. These findings suggest that our experience of time is constructed by the brain rather than directly perceived. The brain creates the experience of now by integrating information from multiple sensory streams that arrive at different times. It constructs the sense of temporal flow by comparing current experiences to memories and expectations. But this raises new puzzles about the relationship between brain time and physical time. If the brain constructs temporal experience, which version of time is real? Is physical time, as described by relativity and quantum mechanics, more fundamental than experiential time as constructed by consciousness? Or do both emerge from more basic processes that are themselves atemporal? Some researchers propose that consciousness and time co-evolve, that neither is more fundamental than the other. As nervous systems become more complex, they develop more sophisticated models of temporal sequence. These temporal models, in turn, allow for more complex forms of consciousness, creating a feedback loop between temporal modeling and conscious awareness. This evolutionary approach suggests that simple organisms like bacteria might have minimal temporal experience, corresponding to their basic ability to respond to environmental changes over time. More complex organisms develop richer temporal experience, including memory, anticipation, and planning. Humans, with our sophisticated brains and cultural transmission, experience the richest temporal flow, including abstract concepts like history, progress, and eternity. From this perspective, time is not discovered by consciousness, but created by it. As consciousness evolves, it brings new forms of temporality into existence. The universe becomes more temporal as it becomes more conscious, with time and awareness co-creating each other through their interaction. This co-evolution of time and consciousness might continue into the future as artificial intelligence systems become more sophisticated. Advanced AI might develop forms of temporal experience that exceed human capabilities, processing information at speeds that make human consciousness seem frozen in comparison, or integrating information over timescales that exceed human lifespans. Such artificial temporal experience might reveal aspects of time that are hidden from human consciousness, Just as our human experience of time might miss important aspects of physical time, artificial consciousness might access temporal dimensions that are closed to biological awareness. But the development of artificial consciousness also raises ethical questions about time and experience. If conscious machines experience time differently than humans, how do we navigate relationships with beings whose temporal experience is fundamentally alien to our own? How do we ensure that artificial consciousness develops in ways that are beneficial rather than harmful? These questions become more pressing as we consider the possibility that consciousness might be substrate independent. If consciousness can arise in any sufficiently complex information processing system, then the universe might already be filled with forms of awareness that we don't recognize as conscious. The physicist Freeman Dyson has speculated that complex astronomical systems like galaxies or galactic clusters might be conscious on timescales vastly longer than human experience. From this perspective, what we call the history of the universe might be just a few moments in the life of a cosmic consciousness that thinks on billion-year timescales. Such speculation pushes the boundaries of scientific inquiry into the realm of the truly speculative, but it illustrates how the question of time's reality opens up vast territories of possibility and mystery that continue to challenge our understanding. Recent developments in quantum field theory have added new dimensions to these mysteries. The discovery of the Higgs boson confirmed the existence of the Higgs field, which gives mass to other particles. But the Higgs field has unusual properties that might be connected to time itself. The Higgs field exists in what physicists call a metastable state, like a ball balanced on a hill that could roll down to a lower energy state at any moment. If the Higgs field transitions to this lower state, it would fundamentally change the properties of space-time throughout the universe. Such a transition might alter the flow of time itself, creating regions where time moves differently or perhaps not at all. The physicist Alan Guth, who developed the theory of cosmic inflation, has suggested that such Higgs field transitions might be constantly occurring throughout the multiverse, creating bubble universes with different physical properties. Some of these bubbles might have different temporal structures, different numbers of time dimensions, or different relationships between time and space. In a multiverse with diverse temporal structures, our own experience of time would be just one possibility among many. Beings in other bubble universes might experience multiple time dimensions, allowing them to move backward and forward in time as easily as we move left and right in space. Others might exist in timeless bubbles, where change occurs, but temporal flow does not. Such multiverse scenarios push our understanding of time to its limits. If every possible temporal structure exists somewhere in the multiverse, then the question of whether time is real becomes meaningless. Time would be real in some regions and unreal in others, with no universal answer to its fundamental nature. But even within our own universe, the nature of time continues to evolve as the cosmos itself evolves. The accelerating expansion of space, driven by dark energy, is gradually changing the structure of space-time. In the far future, this acceleration might lead to a Big Rip scenario where space-time itself tears apart, potentially destroying the fabric from which time emerges. Alternatively, the universe might enter a deeper phase where space-time approaches a steady state with constant expansion. In such a phase, the usual relationship between entropy and time might break down, potentially leading to new forms of temporal experience or the complete disappearance of time's arrow. Some cosmologists speculate about even stranger possibilities. The physicist Paul Steinhardt has proposed cyclic cosmological models, where the universe goes through repeated phases of expansion and contraction. In such models, time might be cyclic rather than linear, with the universe returning to previous states after vast cosmic cycles. Other cosmologists suggest that time itself might have a beginning and end, that the universe might eventually exhaust its capacity for temporal experience and lapse into a changeless state. From this perspective, time would be a finite resource, gradually consumed by the processes that create conscious experience and physical change. These cosmological speculations remind us that the question of time's reality is not just academic, but existential. If time is not fundamental, if consciousness creates temporal experience through its interaction with timeless quantum processes, then the future of time depends on the future of consciousness. As long as conscious beings exist in the universe, time will remain real for them. But if consciousness eventually disappears, either through the heat death of the universe or through other cosmic processes, then time itself might cease to exist. The universe would continue to exist in some sense, but it would be a timeless universe without change, without experience, without the flow of moments that makes existence meaningful for temporal beings. This possibility gives urgency to questions about the preservation and expansion of consciousness in the universe. If consciousness is necessary for time's reality, then protecting and nurturing awareness becomes a cosmic responsibility. The future of time itself might depend on our ability to create sustainable forms of consciousness that can survive the vast changes that await the universe. But perhaps these concerns are premature. Perhaps consciousness is more fundamental and resilient than we imagine. Perhaps the universe naturally tends toward the creation of aware beings, and consciousness will find ways to persist even in the most extreme cosmic conditions. The physicist Frank Tipler has speculated about the possibility of reconstructing all past consciousness in the final moments before the Big Crunch, creating a kind of technological resurrection where every conscious being that ever lived is recreated and allowed to continue existing in accelerated time. Such scenarios might seem like science fiction, but they illustrate the deep connections between consciousness, time, and the ultimate fate of the universe. Whether such speculations prove prophetic or not, they highlight the profound mystery that surrounds temporal experience. We are conscious beings embedded in what might be a timeless universe, creating the flow of time through the very act of awareness. Our existence might be far stranger and more precious than we realize, a brief flowering of temporal consciousness in an eternal, unchanging reality. Yet even as science reveals the strangeness of time, it also reveals the remarkable consistency and beauty of the laws that govern reality. Whether time is fundamental or emergent, real or illusory, the universe operates according to principles that can be discovered and understood through careful observation and reasoning. This consistency gives hope that the mystery of time, however deep, is not beyond human comprehension. Each generation of scientists builds on the discoveries of their predecessors, gradually expanding our understanding of its nature. The questions that seem unanswerable today might yield to future insights and discoveries. The history of science is filled with concepts that once seemed mysterious but are now well understood. The nature of heat, the structure of atoms, the mechanism of heredity. All of these were once profound mysteries that yielded to patient investigation. Perhaps time will join this list of conquered mysteries, its nature finally understood through some future breakthrough in physics or consciousness studies. But even if time's mystery is eventually solved, the solution will likely reveal new mysteries even more profound than those it resolves. This is the pattern of scientific progress. Each answer raises new questions. Each discovery opens new territories for exploration. The investigation of time will likely continue long after our current puzzles are resolved. And perhaps this is as it should be. Perhaps the journey of understanding is more important than any destination, more valuable than any final answer. Perhaps the mystery of time exists not as an obstacle to be overcome, but as a gift to be explored, a source of wonder that connects us to the deepest questions about existence. In contemplating time's possible unreality, we encounter something precious, the ongoing adventure of consciousness meeting mystery, the eternal human quest to understand our place in a universe that continues to exceed our comprehension. Whether time is real or illusory, fundamental or emergent, this quest continues, driven by the same curiosity and wonder that have always motivated human inquiry. As you continue through your daily existence, experiencing the flow of moments that might be the deepest illusion or the most fundamental reality, Carry with you this sense of mystery and wonder. Let it deepen your appreciation for the strange privilege of consciousness, for the gift of awareness in a universe that might transcend all our categories of understanding. Time might not be real, but the search for truth is eternal. And in that search, in that questioning, in that wonder, we find something that transcends time itself, the human spirit encountering the mystery of existence, forever asking, forever seeking, forever awake to the profound strangeness of being conscious beings in an extraordinary universe that continues to surprise us with its depth, beauty, and mystery. But let us venture even deeper into this mystery, exploring realms where the very concept of temporal experience becomes so strange that our ordinary language begins to fail us. Consider the phenomenon known as quantum tunneling, where particles pass through barriers that should be impenetrable according to classical physics. A particle approaching a barrier has some probability of appearing on the other side, as if it had traveled through the barrier instantaneously. But here's where time becomes truly puzzling. Experiments have shown that particles can tunnel through barriers of different thicknesses in the same amount of time. A particle tunneling through a thin barrier takes the same time as one tunneling through a barrier 10 times thicker. This suggests that during the tunneling process, the particle exists in a state outside of normal temporal relationships. Some physicists interpret this as evidence that the particle spends zero time inside the barrier, that it exists in the barrier region for literally no time at all. Others suggest that time itself becomes imaginary during the tunneling process, that particles tunnel through imaginary time before re-emerging into real time on the other side of the barrier. This connection between quantum mechanics and imaginary time is not just mathematical curiosity. Stephen Hawking used imaginary time extensively in his work on black holes and cosmology. In Hawking's approach, the Big Bang singularity disappears when calculated in imaginary time, suggesting that the beginning of the universe might be understood as a transition from imaginary to real time. If time can be imaginary as well as real, what does this tell us about its fundamental nature? Perhaps our normal experience of real time is just one mode of temporal existence, with other forms of time operating in quantum and cosmological realms that remain largely invisible to ordinary consciousness. The mathematician Hermann Minkowski, who first formulated the mathematical structure of space-time, once remarked that space and time individually are shadows of a more fundamental four-dimensional reality. But what if even four-dimensional space-time is itself a shadow of something more fundamental still? String theory, one of the leading candidates for a theory of quantum gravity, suggests that reality has many more dimensions than the four we experience. In string theory, particles are not point-like objects, but tiny vibrating strings existing in 10 or 11 dimensions. Most of these extra dimensions are curled up so small that we cannot directly perceive them, but they influence the behavior of matter and energy in our familiar four-dimensional world. Some versions of string theory suggest that time itself might have extra dimensions, that there could be multiple time-like directions in the fundamental structure of reality. Beings able to perceive these extra temporal dimensions would experience causality in ways utterly foreign to our understanding. They might be able to move backward and forward in time as easily as we move left and right in space, or experience multiple simultaneous timelines flowing in different directions. The mathematics of string theory allows for these exotic temporal structures, but translating them into physical reality remains challenging. If extra time dimensions exist, they must be hidden from our experience in ways similar to how extra spatial dimensions are concealed. Perhaps consciousness itself is somehow constrained to experience only one temporal dimension, even if others exist in the fundamental structure of reality. This possibility connects to ongoing research in consciousness studies on the binding problem, how the brain integrates information from different sources into unified conscious experience. The neuroscientist Christoph Koch has suggested that consciousness requires information integration across both space and time, binding separate neural events into coherent temporal sequences. If consciousness is fundamentally about temporal binding, then our experience of time might be intimately connected to the mechanisms that create unified awareness. Different forms of consciousness might experience different temporal structures, depending on how they integrate information across time. Recent research on altered states of consciousness provides intriguing evidence for this possibility. Studies of psychedelic experiences report profound alterations in time perception, with subjects experiencing moments that seem to last eternities or lifetimes compressed into seconds. Some report experiencing multiple timelines simultaneously, or existing in states where past, present, and future merge into a single eternal now. While these experiences might seem purely subjective, they could be revealing hidden aspects of temporal reality that are normally filtered out by ordinary consciousness. If consciousness constructs temporal experience from more fundamental timeless processes, then altered states might provide glimpses of these underlying processes. The anthropologist Jeremy Narby has documented indigenous shamanic traditions that describe consciousness as capable of traveling through time, accessing information from past and future events. While mainstream science remains skeptical of such claims, they point to widespread human intuitions that consciousness and time have a more complex relationship than our current scientific paradigms suggest. These cross-cultural perspectives on time consciousness reveal the diversity of human temporal experience. The Aymara people of the Andes conceptualize the past as in front of them because it can be known and seen, while the future lies behind them, hidden and unknowable. The Piraha people of the Amazon appear to live in an eternal present, with minimal linguistic structures for discussing past or future events. Such cultural variations in temporal experience suggest that our Western conception of linear time flowing from past through present to future is not universal or inevitable. Different cultures construct different temporal realities, raising questions about which temporal experience, if any, corresponds to the true nature of time. The linguist Benjamin Lee Whorf proposed that language shapes thought, and that speakers of different languages experience reality differently. If Whorf was right, then cultures with different temporal languages might literally inhabit different temporal realities, their consciousness structured by the linguistic categories available to them. Modern neuroscience provides some support for this idea. The brain regions involved in time perception overlap significantly with language processing areas, suggesting that temporal experience and linguistic structure are deeply interconnected. Speakers of languages with complex tense systems show different patterns of neural activity when processing temporal information compared to speakers of languages with simple tense systems. But language might not just shape temporal experience, it might create it. Some philosophers argue that without language, there would be no experience of time, that temporal consciousness emerges from our ability to represent past and future states linguistically. From this perspective, time is not just constructed by consciousness, but specifically by linguistic consciousness. This linguistic approach to time connects to broader questions about the relationship between mathematics and reality. Mathematics, like language, is a system of symbols and rules that allows us to represent and manipulate abstract concepts. The mathematical description of time in physics might not be revealing the fundamental nature of temporal reality, but creating a particular version of it. The physicist Eugene Wigner wrote about the unreasonable effectiveness of mathematics in the natural sciences, wondering why mathematical concepts developed for abstract purposes turn out to describe physical reality so precisely. But perhaps the question is backward. Perhaps mathematics is effective because reality itself is mathematical in nature. If reality is mathematical, then time might be no more or less real than numbers or geometric shapes. Just as the number 7 exists in a mathematical sense without having physical location or duration, time might exist mathematically without being woven into the fabric of physical reality in the way we ordinarily imagine. This mathematical approach to reality has been developed extensively by the cosmologist Max Tegmark, who proposes that reality simply is mathematics, that physical existence is identical to mathematical existence. In Tegmark's mathematical universe hypothesis, every consistent mathematical structure corresponds to a physical reality, and our own universe is just one mathematical structure among infinitely many others. If Tegmark is right, then time exists wherever temporal mathematics is consistent and well-defined. Some mathematical structures might contain multiple time dimensions, others might be completely timeless, and still others might have exotic temporal properties that have no analog in our experience. Our own familiar time would be just one possibility in an infinite mathematical multiverse. But this mathematical approach faces the puzzle of why we find ourselves in this particular mathematical structure rather than any other. If all mathematical realities exist equally, why do we experience this specific version of time rather than some other temporal structure? This is a version of the anthropic principle. We observe the universe we do because it's the kind of universe that can give rise to observers like us. Perhaps beings capable of asking questions about time can only emerge in universes with temporal structures similar to our own. More exotic temporal realities might exist mathematically, but they might not be able to support the kind of complex information processing that consciousness requires. This connects to recent work on the relationship between consciousness and computation. The computer scientist Scott Aaronson has investigated the computational complexity of quantum mechanics, showing that quantum systems can solve certain problems exponentially faster than classical computers. But quantum computation faces a fundamental limitation. Quantum computers cannot solve problems that are classically unsolvable. They can only solve some classically solvable problems much faster. If consciousness is fundamentally computational, then it might face similar limitations. Perhaps conscious beings can only emerge in temporal structures that support certain kinds of computation, limiting the range of temporal realities that can be experienced from the inside. But consciousness might not be fundamentally computational. The mathematician Roger Penrose and anesthesiologist Stuart Hameroff have proposed that consciousness involves quantum processes in microtubules within neurons, processes that cannot be replicated by classical computers. If Penrose and Hameroff are right, then consciousness might have access to aspects of reality that are fundamentally non-computational. This quantum approach to consciousness might explain some of the stranger aspects of temporal experience. If consciousness involves quantum processes, then it might be subject to the same temporal anomalies that affect quantum systems. Quantum superposition, entanglement, and tunneling might all have analogs in conscious experience that remain largely unexplored by current neuroscience. Some researchers have begun investigating these possibilities experimentally. The psychiatrist Ian Stevenson documented thousands of cases of children who claimed to remember previous lives, providing detailed information about deceased persons they could not have learned about through normal means. While such cases remain controversial, they raise intriguing questions about the relationship between consciousness and time. If consciousness can somehow access information from different time periods, then the boundary between past and future might be more permeable than we ordinarily assume. Perhaps memory and precognition are two sides of the same phenomenon, different aspects of consciousness's ability to connect with temporally distant events. Recent experiments in quantum mechanics have revealed phenomena that challenge our normal understanding of temporal causality. The quantum physicist Yakir Aharonov has developed a framework called the two-state vector formalism, which describes quantum systems as being influenced by both past and future boundary conditions. In this approach, the present state of a quantum system depends not just on its past history, but also on its future destiny. This might sound like science fiction, but the two-state vector formalism makes testable predictions that have been confirmed experimentally. Quantum systems seem to have a kind of temporal non-locality that parallels their spatial non-locality. Just as entangled particles can be correlated across space in ways that transcend our normal understanding of locality, quantum systems might be correlated across time in ways that transcend our normal understanding of causality. If consciousness involves quantum processes, then it might exhibit similar temporal non-locality. Perhaps some forms of consciousness can access information from multiple time periods simultaneously, creating experiences that transcend the normal flow from past to future. The physicist Henry Stapp has proposed that consciousness plays a fundamental role in quantum mechanics by selecting which possibilities become actual through the process of observation. If Stapp is right, then consciousness might not just experience time, but actually create it by choosing which potential futures become real. This creative aspect of consciousness might extend beyond individual decisions to the structure of time itself. Perhaps different forms of consciousness create different temporal realities, and our collective human consciousness has shaped the particular version of time that we experience. This connects to some of the stranger predictions of quantum mechanics about the relationship between observation and reality. The many worlds interpretation suggests that all possible outcomes of quantum measurements actually occur, but in different parallel branches of reality. From this perspective, every quantum measurement creates new branches of time, with consciousness somehow selecting which branch it continues to follow. If many worlds is correct, then time has an incredible branching structure, with countless alternative timelines splitting off from every quantum event. The timeline we experience would be just one path through this vast branching structure, selected by the quantum processes occurring in our brains. Alternative versions of ourselves would exist in other branches, experiencing different sequences of events and different versions of history. These alternative selves would be just as real as we are, but causally disconnected from our experience by the branching structure of quantum time. Some researchers have speculated about whether it might be possible to communicate across these quantum branches, or even to transfer consciousness from one branch to another. While such possibilities remain highly speculative, they illustrate the radical implications of taking quantum mechanics seriously as a description of temporal reality. But even within a single timeline, the relationship between consciousness and time might be far stranger than we ordinarily assume. The philosopher Daniel Dennett has argued that consciousness involves multiple parallel processes that create the illusion of a unified stream of experience. If Dennett is right, then our sense of a single timeline might be constructed from multiple temporal processes occurring simultaneously in the brain. Recent neuroscience research supports this view, showing that different aspects of conscious experience, visual processing, auditory processing, emotional response, memory formation, occur on different timescales and in different brain regions. The unified experience of a moment is constructed by integrating information from these multiple temporal streams. This integration process might be more active and creative than we realize. Rather than passively receiving temporal information, consciousness might be actively constructing temporal experience from the available neural data. Different individuals might construct somewhat different temporal realities from the same underlying neural processes. This construction process might explain individual differences in time perception. Some people experience time as moving quickly, others as moving slowly. Some are highly sensitive to temporal sequences, others have difficulty with temporal ordering. These differences might reflect variations in how individual brains construct temporal experience rather than differences in sensitivity to objective time. The study of time perception disorders provides additional insights into this construction process. Patients with certain types of brain damage can lose the ability to sequence events temporally, experiencing all events as occurring simultaneously in an eternal present. Others lose the sense of temporal flow while retaining the ability to order events sequentially. These dissociations suggest that temporal experience involves multiple separable components: the sense of now, the ordering of events, the experience of duration, the feeling of flow. Each of these components might be constructed by different neural mechanisms, and each might have different relationships to physical time. Perhaps most intriguingly, Some patients report experiences of temporal displacement, feeling that they are living in the wrong time period or that they have slipped backward or forward in time. While these experiences are typically interpreted as symptoms of neurological dysfunction, they might be revealing hidden aspects of the relationship between consciousness and time. If consciousness constructs temporal experience rather than simply perceiving it, then alterations in neural function might produce genuine alterations in experienced time rather than just distorted perceptions of objective time. Perhaps these patients are experiencing alternative temporal realities that are normally filtered out by healthy brain function. This possibility connects to broader questions about the relationship between mental illness and alternative realities. Some researchers have suggested that certain psychological conditions might involve access to aspects of reality that are normally hidden from ordinary consciousness. While such ideas remain highly speculative, they point to the possibility that our ordinary temporal experience might be more limited than we realize. The psychiatrist R.D. Laing once suggested that what we call mental illness might sometimes be breakthrough rather than breakdown, access to deeper levels of reality rather than departure from it. If time is not fundamental but constructed by consciousness, then different forms of consciousness might construct different temporal realities, some of which might provide insights into the nature of reality that are inaccessible to ordinary awareness. But even ordinary consciousness might have latent capacities for temporal experience that remain largely undeveloped. Various contemplative traditions describe states of consciousness in which normal temporal experience dissolves, revealing what practitioners describe as timeless awareness or eternal presence. The mystic Meister Eckhart wrote about the eternal now, a moment that contains all of time within itself. The Zen tradition speaks of the gateless gate, a present moment that transcends the ordinary distinction between past and future. These descriptions might be pointing toward genuine aspects of consciousness's relationship to time rather than just poetic metaphors. Recent neuroscience research on meditation and contemplative practices has begun to shed light on these claims. Studies of long-term meditators show altered patterns of brain activity in regions associated with time perception and temporal integration. Advanced practitioners report experiences of expanded present moments, dissolution of temporal boundaries, and access to information that seems to transcend ordinary temporal limitations. While the interpretation of these findings remains controversial, they suggest that consciousness has capacities for temporal experience that go beyond our ordinary understanding. Perhaps the contemplative traditions have discovered genuine features of the relationship between awareness and time that remain largely unexplored by mainstream science. This connects to broader questions about the evolution of consciousness and its future development. If consciousness and time co-evolve, as some researchers suggest, then the future evolution of awareness might involve new forms of temporal experience that transcend our current limitations. Advances in neurotechnology might accelerate this evolution. Brain-computer interfaces are already allowing direct neural control of external devices, and future developments might allow more direct manipulation of neural processes involved in time perception. Such technologies might eventually allow for enhanced temporal awareness, expanded present moments, or even access to information from different time periods. But technological enhancement of temporal consciousness raises profound ethical questions. Who would have access to such technologies? How would enhanced temporal awareness change the nature of human experience and social relationships? What would happen to individuals with ordinary temporal consciousness in a world where others had access to expanded temporal awareness? These questions become more pressing as we consider the possibility of uploading consciousness to digital substrates. If consciousness can be transferred to computer systems, then it might be possible to create artificial beings with temporal experience radically different from our own. Digital consciousness might experience thousands of years of subjective time in seconds of physical time, or exist in states where multiple timelines are experienced simultaneously. Such artificial beings would face the question of temporal identity in acute form. If a digital consciousness can be copied, which copy has continuity with the original? If the consciousness can be paused and restarted, what happens to temporal experience during the pause? If multiple copies exist simultaneously, do they share a common temporal reality or inhabit separate time streams? These questions about digital consciousness connect to broader philosophical problems about personal identity and temporal continuity. The philosopher Derek Parfit argued that personal identity is not what matters for survival, that what we really care about is psychological continuity rather than metaphysical identity. If Parfit is right, then questions about temporal identity might be less important than questions about temporal experience. Perhaps what matters is not whether time is real or whether temporal continuity is preserved, but whether conscious beings can continue to experience meaning, growth, and relationship within whatever temporal structures they inhabit. From this perspective, the question of time's reality becomes secondary to questions about how to create fulfilling temporal experience within the constraints of whatever reality we actually inhabit. This pragmatic approach to temporal questions connects to broader themes in philosophy and science about the relationship between truth and utility. Perhaps some questions are more important for their practical implications than for their theoretical answers. Perhaps the question of time's reality is valuable not because it has a definitive answer, but because investigating it expands our understanding and opens new possibilities for experience and action. The investigation of time's nature has already led to practical technologies that have transformed human experience. GPS satellites must account for relativistic time dilation to maintain accuracy. Quantum technologies rely on temporal properties of quantum systems that transcend classical understanding. Medical technologies use insights from neuroscience research on time perception to treat temporal disorders. Future investigations might lead to even more dramatic applications. Understanding the relationship between consciousness and time might allow for new forms of therapy for depression, anxiety, and other conditions that involve distorted temporal experience. Insights into quantum temporal phenomena might lead to new technologies for computation, communication, and energy production. But perhaps the most important applications will be existential rather than technological. As we deepen our understanding of time's nature, we might develop new ways of relating to mortality, change, and the passage of time in our personal lives. We might discover new forms of meaning and purpose that are compatible with time's possible unreality. If time is not fundamental, then perhaps death is not the absolute ending it appears to be. If consciousness is connected to timeless quantum processes, then something essential about awareness might persist even when biological processes cease. This doesn't necessarily imply personal survival after death, but it might suggest that consciousness itself is more fundamental and enduring than we ordinarily assume. Similarly, if time emerges from consciousness rather than being imposed upon it, then perhaps we have more agency in shaping our temporal experience than we realize. Rather than being passive victims of time's passage, we might be active participants in creating the temporal reality we inhabit. This participatory view of time consciousness has profound implications for how we approach life's challenges and opportunities. Rather than seeing ourselves as moving through fixed timelines toward predetermined futures, we might understand ourselves as continuously creating temporal reality through our choices, attention, and awareness. The quantum physicist John Wheeler expressed a similar idea in his concept of a participatory universe, where conscious observation plays a fundamental role in creating reality. If Wheeler was right, then we are not just observers of temporal reality, but active participants in its ongoing creation. This creative aspect of temporal consciousness might extend beyond individual experience to collective and cultural levels. Perhaps human societies collectively create shared temporal realities through their institutions, practices, and beliefs. Different cultures might literally inhabit different temporal worlds, shaped by their collective choices about how to organize and experience time. From this perspective, our modern Western emphasis on clock time, efficiency, and linear progress represents just one way of collectively constructing temporal reality. Alternative approaches, such as indigenous circular time concepts or contemplative traditions emphasizing eternal presence, represent different collective experiments in temporal consciousness. As our global civilization faces challenges that require long-term thinking and planning, perhaps we need to develop new forms of collective temporal consciousness that can encompass longer time scales and more complex temporal relationships. Climate change, nuclear waste disposal, space exploration, and the development of artificial intelligence all require thinking across timescales that exceed normal human experience. Perhaps future human societies will develop institutions and practices that support expanded temporal awareness, allowing for collective decision-making that encompasses generations or centuries. Such temporal expansion might be necessary for navigating the challenges and opportunities that await our species. But even as we speculate about future developments in temporal consciousness, we must remember that we are embedded in the mystery we are trying to understand. We are temporal beings investigating time, conscious entities studying consciousness, finite creatures contemplating infinity. This creates both opportunities and limitations in our approach to these fundamental questions. The opportunities arise from the fact that we have direct access to temporal consciousness through our own experience. We don't just study time from the outside, but participate in temporal reality from the inside. This gives us insights into temporal consciousness that might be inaccessible to purely objective investigation. The limitations arise from the fact that our own temporal embedding might blind us to aspects of time that could only be visible from outside temporal experience. We might be like fish trying to understand water, so immersed in temporal reality that we cannot step outside it to see it clearly. But perhaps these limitations are not absolute. Perhaps through careful investigation, creative thinking, and openness to alternative perspectives, we can gradually transcend the limitations of our temporal embedding and achieve deeper understanding of time's nature. The history of science provides examples of how human understanding has transcended apparent limitations. We have learned to see beyond the horizon of our immediate experience, to understand realms far larger and smaller than ordinary perception can access, to grasp concepts that initially seemed beyond human comprehension. Perhaps the nature of time will eventually join the list of mysteries that human inquiry has successfully illuminated, or perhaps time's mystery will deepen as our understanding expands, revealing new depths of strangeness that we cannot currently imagine. Either way, the investigation continues, driven by the same curiosity and wonder that have always motivated human inquiry. We remain conscious beings embedded in temporal reality, questioning the nature of the time we inhabit, seeking to understand our place in a universe that continues to exceed our comprehension. In this ongoing investigation, each moment of questioning becomes part of the mystery being investigated. Each thought about time occurs within time. Each insight into consciousness arises from consciousness. Each step toward understanding temporal reality is itself a temporal event. We are not separate from the mystery we study, but intimately embedded within it. This embedding gives our investigation both urgency and poignancy. We are temporary beings studying eternity, mortal creatures contemplating permanence, brief flickerings of consciousness investigating the nature of awareness itself. Our questions about time are also questions about our own existence, our own meaning, our own place in the larger scheme of things. Whether time proves to be real or illusory, fundamental or emergent, our temporal existence remains precious and meaningful. The moments of wonder, connection, and understanding that arise from our investigation are valuable regardless of time's ultimate status. The journey of questioning enriches the questioner, regardless of the destination, and perhaps this enrichment is the deeper purpose of our temporal existence. Perhaps we are here not just to solve the mystery of time, but to experience the beauty and wonder of conscious inquiry itself. Perhaps the universe has evolved conscious beings not just to understand reality, but to celebrate it, to marvel at its depths and complexities, to find meaning and joy in the very process of questioning. From this perspective, time's mystery becomes not a problem to be solved, but a gift to be treasured. Whether real or illusory, time provides the stage on which consciousness encounters reality, the medium through which wonder and understanding emerge, the framework within which meaning and purpose unfold. As you continue your journey through the moments that comprise your existence, whether those moments prove to be fundamental features of reality or elaborate constructions of consciousness, cherish the privilege of participating in this greatest of all adventures, the encounter between awareness and mystery, the ongoing dialogue between consciousness and the cosmos, the eternal human quest to understand and appreciate the extraordinary universe of which we are a part. Yet even as we contemplate these grand mysteries, time manifests itself in the most intimate aspects of our biological existence. Within every cell of your body, molecular clocks are ticking, keeping time with a precision that rivals the most sophisticated atomic timepieces. These circadian rhythms, evolved over billions of years, orchestrate everything from your sleep-wake cycles to the release of hormones, from DNA repair processes to the regulation of body temperature. The suprachiasmatic nucleus, a tiny cluster of neurons in your hypothalamus containing fewer than 50,000 cells, serves as your body's master timekeeper. This biological clock synchronizes itself to the external world through light signals transmitted from your eyes, but it continues to tick even in complete isolation from environmental time cues. Cave-dwelling experiments have shown that humans maintain roughly 24-hour rhythms even when deprived of all external temporal information, suggesting that timekeeping is built into the fundamental architecture of consciousness itself. But here's where biological time becomes mysterious. These molecular clocks don't simply respond to time, they appear to create it. The oscillations of circadian genes like period and clock don't just mark the passage of time, they generate the temporal framework within which cellular processes unfold. Without these molecular oscillators, biological time would cease to exist at the cellular level, even if physical time continued unchanged. This biological generation of time extends beyond individual organisms to entire ecosystems. Trees coordinate their seasonal changes through molecular timing mechanisms that respond not just to current conditions, but to the temporal patterns of previous years. Some trees appear to maintain internal calendars spanning decades, suggesting that biological systems can embody long-term temporal patterns that transcend individual lifespans. The monarch butterfly presents an even more remarkable example of biological time transcending individual existence. The butterflies that migrate south in the fall are not the same individuals that return north in the spring. The migration spans multiple generations, yet somehow the population maintains navigational knowledge that requires temporal information spanning months and thousands of miles. The butterflies seem to inherit not just genetic information, but temporal information, carrying within their DNA the memory of seasonal timing patterns that no individual butterfly could have directly experienced. This inheritance of temporal patterns suggests that biological evolution itself might be a process of temporal learning, where species gradually incorporate temporal information about their environments into their genetic and developmental programs. From this perspective, DNA is not just a blueprint for building organisms, but a kind of temporal memory system, encoding information about time patterns that proved successful for ancestral organisms. The human brain represents perhaps the most sophisticated temporal learning system that evolution has produced. Your brain doesn't just exist in time, it is fundamentally organized around temporal processing. The very architecture of neural networks embodies temporal relationships with synaptic connections that strengthen or weaken based on the timing of neural activity. The phenomenon known as spike timing dependent plasticity reveals how central time is to neural function. When one neuron fires shortly before another, the connection between them strengthens. When the timing is reversed, the connection weakens. This means that learning, memory, and neural development all depend critically on temporal relationships between neural events that occur on millisecond time scales. But the brain's temporal processing operates across multiple time scales simultaneously. While individual neurons process information on millisecond timescales, neural assemblies coordinate their activity across seconds, and larger brain networks synchronize their oscillations across minutes or hours. Your brain is constantly integrating temporal information across these multiple scales to create coherent conscious experience. This multi-scale temporal processing might explain some of the mysteries of consciousness. The binding problem, how the brain creates unified conscious experience from distributed neural activity, might be fundamentally a problem of temporal coordination. Consciousness might emerge when neural processes across different brain regions synchronize their temporal patterns in specific ways. Recent research using brain imaging techniques has revealed that consciousness involves complex patterns of temporal coordination between different brain networks. During conscious perception, neural oscillations in different frequency bands become temporally aligned across widespread brain regions. When consciousness is lost during anesthesia or sleep, these temporal coordination patterns break down, suggesting that consciousness itself might be a form of temporal organization in neural activity. This temporal view of consciousness has profound implications for our understanding of mental disorders. Many psychological conditions involve disruptions in temporal processing. Depression is associated with alterations in circadian rhythms and difficulties with temporal perspective, with patients often experiencing time as moving slowly or being trapped in repetitive temporal loops, focused on past failures or future fears. Anxiety disorders frequently involve temporal displacement, with consciousness becoming fixated on potential future threats rather than present reality. The anxious mind creates elaborate temporal scenarios about what might happen, experiencing stress responses to events that exist only in imagined futures. Attention deficit disorders involve difficulties with temporal sequencing and the ability to maintain focus across time intervals. The ADHD brain appears to process temporal information differently, leading to challenges with planning, time estimation, and maintaining attention across extended periods. Even more dramatic are the temporal disturbances seen in psychotic conditions like schizophrenia, where patients may experience time as fragmented, non-linear, or populated by events from multiple temporal periods simultaneously. Some patients report living in several time periods at once, or experiencing their life history as jumbled and out of sequence. These clinical observations suggest that mental health itself might depend on the ability to construct coherent temporal experience. Psychological well-being might require not just the absence of symptoms, but the presence of healthy temporal consciousness, the ability to integrate past experience, present awareness, and future possibilities into a meaningful narrative structure. This narrative dimension of temporal consciousness points to another crucial aspect of how time emerges from awareness. Humans are fundamentally storytelling creatures, and stories are inherently temporal structures. We understand our lives and ourselves through narratives that give meaning to temporal sequences of events. The stories we tell about our past shape our present identity and influence our future choices. But these stories don't simply record what happened. They actively construct temporal meaning by selecting certain events as significant, organizing them into causal sequences, and projecting them forward into anticipated futures. Different individuals construct quite different temporal narratives from similar life experiences. Some people create stories of progress and growth, interpreting challenges as opportunities for development. Others construct narratives of decline or repetition, experiencing their lives as cycles of failure or stagnation. These narrative differences might reflect fundamental variations in how individuals construct temporal experience. People with more flexible narrative abilities might literally inhabit richer temporal realities, with access to more diverse possibilities for interpreting and responding to their experience. The construction of temporal narratives also occurs at cultural and historical levels. Entire civilizations create collective stories about time that shape how their members experience temporal reality. Some cultures emphasize cyclical time, viewing history as repeating patterns that return to earlier conditions. Others emphasize linear progress, seeing time as moving toward improved future states. These cultural differences in temporal narrative have practical consequences for how societies approach challenges like environmental degradation, technological development, and social change. Cultures with cyclical time concepts might be more attuned to sustainability and long-term thinking, while cultures emphasizing linear progress might be more focused on innovation and growth. The digital age has introduced new forms of temporal experience that challenge traditional narrative structures. Social media creates fragmented temporal streams where past and present intermingle in non-sequential ways. Digital communication occurs in compressed timeframes that blur the boundaries between immediate and delayed responses. Virtual worlds allow people to experience multiple temporal realities simultaneously. These technological changes in temporal experience might be creating new forms of consciousness that process time in fundamentally different ways. Young people who have grown up with digital technology appear to have different temporal processing abilities than older generations, with enhanced capacity for multitasking and rapid task switching, but potentially reduced ability to maintain sustained attention across longer time intervals. The emergence of artificial intelligence systems that can process information at speeds vastly exceeding human capabilities raises even more profound questions about the future of temporal consciousness. Advanced AI systems might experience subjective years or decades in seconds of human time, or process multiple temporal streams simultaneously in ways that no biological consciousness could match. If such artificial consciousness emerges, it would face novel questions about temporal identity and continuity. An AI system that can be copied, paused, accelerated, or merged with other systems would inhabit a temporal reality utterly unlike human experience. Such beings might develop forms of temporal consciousness that we cannot even imagine from our biological perspective. But even without artificial intelligence, human temporal consciousness continues to evolve through cultural and technological development. Modern transportation allows us to experience multiple time zones within single journeys, creating forms of temporal displacement that were impossible for our ancestors. Global communication networks create shared temporal experiences that span continents and cultures. Space exploration will likely create even more exotic forms of temporal experience. Astronauts on long-duration space missions already experience altered relationships to Earth-based time cycles. Future interstellar travel would involve relativistic effects that could disconnect space travelers from Earth's temporal reference frame entirely. If humans eventually establish permanent settlements on other planets, they would develop local temporal cultures adapted to different day-night cycles and seasonal patterns. Martian humans might develop temporal consciousness structured around the 24.6-hour Martian day, gradually diverging from Earth-based temporal experience. These possibilities remind us that human temporal consciousness is not fixed, but continues to evolve in response to changing conditions and new experiences. Just as our ancestors developed new forms of temporal awareness as they transitioned from hunter-gatherer to agricultural to industrial societies, we may be in the midst of developing new forms of temporal consciousness adapted to our technological and global age. The speed of modern life has certainly altered human time perception in noticeable ways. Many people report feeling that time passes more quickly than it did in previous decades, that days and years blur together in ways that make it difficult to form distinct temporal memories. This acceleration of experience time might reflect changes in how we structure our attention and activities, or it might indicate more fundamental shifts in how consciousness processes temporal information. Research on time perception shows that subjective time speeds up when we are busy and engaged with complex tasks, but slows down when we are bored or paying close attention to temporal passage. The modern lifestyle, with its emphasis on productivity and constant stimulation, might be creating conditions that systematically accelerate subjective time. But there are also countervailing forces that can slow down temporal experience. Mindfulness practices, which emphasize present moment awareness, can dramatically alter time perception. Experienced meditators report that meditation practice expands their sense of the present moment, allowing them to experience more within given temporal intervals. The phenomenon of flow states, where individuals become completely absorbed in challenging activities, creates another form of altered temporal experience. During flow states, people often report that time seems to stop or become irrelevant, that hours can pass without awareness, yet the experience feels timeless rather than rushed. These altered states of temporal consciousness might provide clues about the fundamental nature of time and awareness. If consciousness can experience time in such radically different ways, depending on attention, activity, and mental state, then perhaps the normal experience of temporal flow is just one possible mode of temporal consciousness rather than a direct perception of objective time. Dream states offer another window into alternative forms of temporal consciousness. Dreams often involve complex temporal distortions, events that seem to unfold over long periods but occur during brief REM episodes, narrative sequences that jump between different time periods without logical transition, or experiences of being multiple ages simultaneously. Some researchers have suggested that dream consciousness accesses more fundamental forms of temporal processing that are normally filtered out by waking awareness. In dreams, the usual constraints of causal sequence and logical temporal order are relaxed, potentially revealing underlying temporal possibilities that remain hidden in ordinary consciousness. The study of memory provides additional insights into how consciousness constructs temporal experience. Memory research has shown that recollection is not like playing back a recording, but involves active reconstruction of past events using available information and current knowledge. Each time we remember something, we slightly alter the memory, blending past and present in ways that continuously reshape our personal temporal landscape. False memories can feel as real as accurate memories, suggesting that the brain's memory systems cannot distinguish between events that actually occurred and events that were vividly imagined or suggested. This malleability of memory raises profound questions about the relationship between remembered time and actual time. If our sense of personal history depends on memories that are continuously reconstructed and potentially inaccurate, then our experience of temporal continuity might be more constructed than we realize. The past that shapes our identity might be partly fictional, a story created by memory systems that prioritize meaning and coherence over accuracy. This reconstructive nature of memory might explain why people's recollections of the same events can differ so dramatically. We might not be disagreeing about what happened, but literally inhabiting different temporal realities created by different memory reconstruction processes. The social dimension of memory adds another layer to temporal construction. Shared memories, cultural narratives, and historical records create collective temporal realities that individual memory draws upon. But these collective temporal constructions are themselves fluid and changing, constantly reinterpreted by each generation according to their contemporary concerns and perspectives. Historical revisionism is not just an academic exercise, but an active process of temporal reconstruction that occurs continuously in human societies. Each generation creates new versions of the past that support their understanding of the present and their aspirations for the future. This social construction of time extends to future-oriented temporal experience as well. Cultural expectations, economic systems, and political structures create shared frameworks for anticipating and planning future events. These collective temporal constructions shape individual behavior and decision-making in profound ways. The phenomenon of self-fulfilling prophecy illustrates how expectations about future events can influence the events themselves. When enough people believe that certain futures are likely, their actions based on those beliefs can make the anticipated futures more probable. In this way, consciousness doesn't just predict the future, but participates in creating it. Financial markets provide a clear example of how collective temporal consciousness shapes reality. Market prices reflect the aggregate expectations of countless individuals about future economic conditions. These expectations influence investment decisions that, in turn, affect the actual economic conditions that unfold. The future envisioned by the market participants becomes partly self-creating through their responses to their own temporal projections. Similarly, cultural movements and social changes often begin as shifts in collective temporal consciousness, new visions of possible futures that inspire coordinated action. The civil rights movement, environmental activism, and technological innovation all involve groups of people sharing new temporal narratives and working to make anticipated futures more likely. This creative aspect of temporal consciousness suggests that humans are not just observers of time, but active participants in its unfolding. Through our individual and collective choices, we influence which possibilities become actual, which futures emerge from the vast space of potential realities. The responsibility that comes with this creative power over temporal reality is both inspiring and sobering. If consciousness plays a fundamental role in shaping the futures that emerge, then how we think about time, how we construct temporal narratives, and how we make choices based on temporal projections all become matters of profound importance. Climate change represents perhaps the greatest challenge facing human temporal consciousness today. The problem requires thinking across timescales that exceed normal human experience, decades for policy implementation, centuries for full climate system responses, and millennia for some environmental feedbacks. Yet the psychological mechanisms that drive behavior operate on much shorter timescales, focused on immediate rewards and near-term consequences. Successfully addressing climate change might require developing new forms of collective temporal consciousness that can encompass these longer timescales while remaining connected to immediate experience and motivation. This represents an evolutionary challenge for human consciousness, learning to care about and act on temporal realities that exceed the scope of individual lifespans. Similar challenges arise with other long-term risks facing human civilization, such as nuclear waste disposal, asteroid impacts, and the potential development of artificial general intelligence. All of these challenges require forms of temporal thinking that transcend normal human time horizons, while remaining grounded in present moment decision-making. Perhaps addressing these challenges will drive the next phase of human temporal consciousness evolution, just as agricultural development required new forms of seasonal thinking and industrial development required new forms of mechanical time coordination. We might be entering an era that requires new forms of geological and cosmic temporal awareness, the contemplation of deep time, the billions of years of Earth's history, the eventual death of the sun, the ultimate fate of the universe, can be overwhelming from the perspective of individual human consciousness, yet it can also be liberating, placing current concerns in broader contexts and revealing new possibilities for meaning and purpose. From a deep time perspective, human civilization is incredibly young, and conscious life itself might still be in its earliest developmental stages. If consciousness continues to evolve and expand, the forms of temporal awareness that emerge in the future might be as far beyond current human experience as our temporal consciousness is beyond that of simpler organisms. This evolutionary perspective suggests that questions about time's reality might themselves evolve as consciousness develops new capacities for temporal experience. Questions that seem fundamentally unanswerable from current perspectives might become tractable from future standpoints, while new questions emerge that we cannot currently formulate. The investigation of time's nature is thus not just an intellectual exercise, but part of the ongoing evolution of consciousness itself. By questioning time, exploring alternative temporal realities, and pushing the boundaries of temporal understanding, we participate in the universe's growing self-awareness. This self-reflective dimension of temporal investigation creates a kind of feedback loop where consciousness studies itself studying time, where temporal beings investigate temporality, where the questioner and the questioned are intimately interconnected. This recursive structure might be fundamental to the nature of consciousness and time themselves. Perhaps consciousness and time are not separate phenomena that happen to be related, but aspects of a more fundamental process of self-organizing complexity that gives rise to both awareness and temporality simultaneously. From this perspective, the question of whether time is real becomes a question about the reality of consciousness, and vice versa. Recent work in complexity science and systems theory provides frameworks for understanding how complex phenomena like consciousness and time might emerge from simpler underlying processes. Emergence occurs when interactions between simple components give rise to system-level properties that cannot be reduced to the properties of the components themselves. Time and consciousness might both be emergent properties of complex information processing systems, arising when certain types of organization and interaction patterns become sufficiently sophisticated. This would explain why time seems so fundamental to conscious experience while being problematic at the level of fundamental physics. The science of complexity also reveals how emergent properties can become causally efficacious, influencing the lower-level processes from which they emerge. Even if time emerges from timeless quantum processes, it can still have real causal power in organizing and coordinating complex systems like brains and ecosystems. This downward causation from emergent properties to underlying processes might explain how consciousness can influence physical reality, how mental states can affect neural activity, and how temporal experience can shape the quantum processes that occur in neural systems. If consciousness and time are emergent properties that can causally influence their own underlying substrates, then they might be capable of directing their own evolution and development. Conscious temporal beings might be able to participate in shaping the very processes that give rise to consciousness and temporality. This participatory relationship between consciousness, time, and the physical processes that support them, how we think about time, how we construct temporal narratives, and how we organize temporal experience might all influence the evolution of temporal consciousness itself. From this perspective, investigations into time's nature are not just attempts to understand a fixed reality, but active participation in the ongoing creation of temporal reality. The questions we ask, the experiments we perform, and the theories we develop all become part of the process through which time and consciousness co-evolve. This makes the current era of temporal investigation particularly significant. For the first time in human history, we have scientific tools sophisticated enough to probe the quantum foundations of reality, computational models complex enough to simulate complex temporal processes, and global communication networks that allow for unprecedented coordination of temporal research. The convergence of quantum mechanics, neuroscience, complexity theory, and consciousness studies is creating new possibilities for understanding temporal reality that were unimaginable even a few decades ago. We might be approaching breakthrough insights that could fundamentally transform our relationship to time and temporal experience. Yet even as scientific understanding advances, the mystery of temporal experience remains profound and personal. Each individual consciousness continues to face the immediate reality of moment-to-moment temporal flow, regardless of what physics or neuroscience might reveal about time's ultimate nature. This creates an interesting tension between the scientific investigation of time and the lived experience of temporality. Science might show that time is emergent, constructed, or even illusory, but conscious beings must still navigate the temporal realities of their immediate experience, making decisions, forming memories, anticipating futures, and creating meaning within whatever temporal structures they inhabit. Perhaps this tension is productive rather than problematic. Perhaps the ongoing dialogue between scientific understanding and lived experience drives both forward, creating new possibilities for temporal consciousness that neither could achieve alone. The scientific understanding of time's nature might eventually become sophisticated enough to inform practices that can enhance temporal experience, methods for expanding present moment awareness, techniques for improving temporal integration and memory, approaches for developing healthier relationships to mortality and change. Similarly, the exploration of temporal experience through contemplative practices, artistic expression, and conscious experimentation might reveal aspects of temporal reality that remain invisible to purely scientific investigation. The integration of these different approaches to understanding time might eventually yield forms of temporal wisdom that transcend the limitations of any single perspective. Such temporal wisdom might be essential for navigating the challenges and opportunities that await conscious beings in an evolving universe. As you continue through the temporal experiences that constitute your existence, you participate in this grand investigation, not just as an observer, but as an active researcher. Your moment-to-moment choices about attention, memory, and anticipation contribute to the ongoing evolution of temporal consciousness. The quality of presence you bring to immediate experience, the narratives you construct from temporal events, the future possibilities you envision and work toward, all of these become part of the larger process through which consciousness and time continue to co-create each other. In this sense, every moment of conscious experience is both an instance of temporal reality and an experiment in temporal possibility. Through the simple act of aware temporal existence, you contribute to the universe's growing understanding of its own temporal nature. This contribution is precious, regardless of what ultimate answers might emerge about time's fundamental status. Whether time proves to be real or constructed, fundamental or emergent, your conscious participation in temporal reality remains a remarkable and meaningful phenomenon. The privilege of experiencing temporal flow, of participating in the unfolding of moments, of being aware of change and continuity within your own experience, these constitute irreplaceable aspects of what it means to be a conscious being in this particular universe. As the mystery of time continues to deepen and evolve through scientific discovery and conscious exploration, your own temporal journey remains uniquely valuable, a singular perspective on the great questions that consciousness brings to its encounter with reality. Whether time is ultimately real or illusory, whether consciousness creates temporal experience or discovers it, whether the universe is fundamentally temporal or eternally timeless, the investigation itself enriches both the investigator and the reality being investigated. In questioning time, we discover ourselves. In exploring temporal consciousness, we participate in the universe's effort to understand itself. In living temporally aware lives, we contribute to the ongoing creation of whatever temporal reality emerges from the mysterious intersection of consciousness, quantum mechanics, and cosmic evolution. The adventure continues, moment by moment, question by question, wonder by wonder, in the eternal now that might be all there ever was, is, or will be.